Let him join. We'll start.
Everyone is here, sir.
If the slides are visible. Hello.
Yes, sir.
So we'll start with the modes of loading. Yesterday where we stopped, I told you this is one of the milestone in the fracture mechanics. I told you the importance of the loadings. Okay, there are actually three modes, the types of moding. Okay, mode 1, mode 2, and mode 3. Or sometimes they say mode 1, mode 2, mode 3. So mode 1 means it is something like, crocodile mouth opening. That is suppose you apply load like this. So the failure is like this. That is mode 1. Once you apply the load like this, okay, this is the cracked surface. It keep on expanding. Okay. Mode 2 means slipping, because you are pushing and you are pulling like that. So this is again failure surface, but it keep on slipping the things. So your failure surface will increase. This is mode 2. And mode 3 is tearing mode. Okay, you are pulling like this, pulling like this, just like a paper. Okay, you are actually tearing. There is a paper, no? You just tearing means paper will break like this or tear like this. These three type of moldings are very, very important, because the whole fracture mechanics we are going to discuss about these points only. If you see, okay, there are factors called, okay, stress intensity factors. Similarly, fracture toughness. These are all very, very important. On the other hand, you will have the toughness parameter. Then energy release rate. So energy release rate is G1, G2, G3. Here G1C, G2C, G3C. I told the very beginning, there are two approaches in fracture mechanics. One is energy approach, another one is stress based approach. Once you design for energy based approach, then you have to go with, okay, energy release rate failure mode, failure criteria or something like that. When you go with the stress mode means your failure you have to specify through stress intensity factor. So all these three modes, the G1 means, okay, energy is coming out by mode 1. K1 means stress intensity from mode 1. G2 means energy release rate through mode 2 or stress release factor by mode 2. Similarly, G3 energy released by mode 3 or K3 stress factor created because of this one, intensity factor. So you go with a energy method, you will be concerned with G1, G2, G3. If you go with the stress intensity or stress based thing, then it is something like K1 based. K means stress intensity factor. G means energy release rate. On the other hand, you can see here critical energy release rate. It's called toughness. Critical, stress intensity factors. C means critical. Now, when the fracture will really, because I told when all the fracture mechanics, we are considering one initial discontinuity. Always. Okay, there will be an initial flaw or initial discontinuity. With that only we are really analyzing, because I told when the material is being made, it got some crack. So our analysis starts from there is a crack. There is no material without any crack. That way we are not analyzing it. So with the discontinuity or with the crack or with the flaw, we are estimating how much I can utilize that particular material, component, object. So what is this critical factor means? It is something like the stress strain graph for a typical mild steel, very well. Okay, so this is your sigma u. This stress corresponds to sigma u. So there will be stress corresponding to sigma y. This is material. This is material stress strain. Suppose I have a beam. Beam is made of mild steel. Okay, I am applying a load. So due to that, again, stress strains are creating. Okay, this is a stress strain for this material, steel. This is a stress strain because of the load when you are applying, how much stress is creating inside the material. This is different, this is different. Because this stress strain graph is being plotted from the experimental point of view, laboratory, which will give you using a piece of material has been taken, and from that it has been applied the universal testing machine, the respective AES standard procedure. From that one can plot it. From this one can understand that how much the stress can take. So this is the ultimate or stress critical. So what is this stress strain? When the body is subjected with forces, then it is creating. Then this is again a stress, instantaneous stress at that particular point in time, at a particular location. So when here you can say failure will come, this instantaneous stress will be less than sigma u, isn't it? No. So sigma u is what? Experimentally tested material character. Sigma is on field. Similarly, the G's and all energy release rate because of the load. G1C means it is the resisting capacity like sigma u. Similarly, stress intensity factor. This is which is coming real time, like here. This example. What is this? This is the resistance, which actually they will create this number from the lab for this particular material. What is the toughness, fracture toughness parameter? So when a failure will come or when it will not come, our K1, if it is less than K1C, then no failure. If K1 greater than K1C, failure. Here you are saying no, sigma, okay, is greater than sigma u, failure. Same concept. Energy, instantaneous energy which is coming out of the load is greater than its 1 means that mode, then failure will come, because this is critical. This is instantaneous, greater than that, failure will come. G1 is less than G1C, no failure. Understood this concept?
Yes, sir.
This is the final goal. Okay, when a material will start failure in the fracture field. So every material they will test in the laboratory about its fracture parameter for mode 1, mode 2, mode 3. How they will find mode 1, how they will mode 2 and all, we have set of procedures are available. Set of procedures are available. Similarly, energy. Every material you will find these things. This is laboratory tested toughness value, critical value. So the real value or the on-site value should be less than the experimentally tested ultimate values. If it is more, failure will take place. This is how the design process goes. I hope you understood. So, at the end of the course, okay, something like your course objective, something like that, okay. So, what is your course objective? What you will learn means, so you can, okay, answer all these questions. What is the critical crack length? Okay, what is the critical crack length? So, as we discussed, suppose I have a beam, okay, there is a crack. So you are applying a sinusoidal load or fatigue load. So the crack is growing. So initially I will have one length. Then crack will grow. So okay, L plus L growth. But one point in time, okay, when you apply the load, okay, even the crack, if you see I'm expanding, initial crack is like this, the crack is growing something like this. So it need not touch this particular thing. So this particular L will become LC, automatically you will get failure. That is called the critical crack length. Once it reaches that particular number, the next instantaneous of load, the things will fail. That is called the critical length of the crack. Okay, so you can estimate, you will estimate end of the day. And again, for the given crack length, what is the residual strength? Suppose I have a component. Okay, I have a component. So, what's the residual strength? Suppose this is the load without crack. So, if I operate the particular component without any crack, with crack, okay, if there is a crack, inside, obviously the strength will come down. Okay, so what is that estimation? If with crack, without crack, how much the strength came down? That estimation one can make. And what is the time? So I told you, a crack is taking from here to here, from here to here. How much time it is taken? Or how many cycles it has taken? So that I can operate my aeroplane till that many cycles or till that much time. That time estimation. How to design NDT schedule? How to design it? Because by having the fracture in any body, I should do actually in every body of the component, that is aircraft, we have thousands of components, isn't it? No? So we know each component may, may subject to some kind of crack or some kind of flaw, discontinuity. We know the severity of the location, structure, manufacturing process, so that maybe 100 cycle of the aircraft, I can take up one particular component, I will test for NDT. If I find there is no crack formation, I may refit into the aeroplane. So that schedule, how can I issue that? How can I know that schedule? Unless otherwise, if I don't have any much analysis information on that, so that is for the fracture techniques. Then crack branching. Why that crack branching is happening? Okay, all these things you can get. And also, if there is a crack there, so a lot of the material subjected to a lot of friction, vibration kind of things, because it's a very serious offense when the crack is there in a body. So how can I minimize the dissipating the energy so that the system will be more stable or less rate of crack growth? So this kind of study one can get end of the day. Okay, so you can see here the new test for fracture mechanics. So this is a component. Your component is having initial flaw. Okay, you can see here. Okay, this is the initial flaw. Then after you apply the load, okay, the crack grown here. This is the crack growth. Crack grown here. This is the crack growth. Okay, so this is A means crack length, N means number of cycles. So crack length A means this is the crack length. Now this is number of cycles. So load, I am applying this load, no? 1, 2, 3. It goes like this. N, load, number of cycles. When I apply, I continuously monitoring using the ultrasonic probe. Keep on watching the crack growth. You can see this particular graph. This graph is plotted. Okay, the number of cycles with respect to crack length. Number of cycles with respect to crack length. So I have, three specimens. Okay, I have three specimens. 1, 2, 3. Same material, same dimension, but one is small crack length, another is bigger crack length, another is bigger crack length. That's the only thing. Okay, same load, same material, same geometry. Only crack length is more. So here L, okay, here L plus del, here L plus 2 del, like that. Okay. So these three, I am applying science order, same load, same fashion. Okay. So I told you, no, you keep on apply the load. Because of the crack is there, then crack will start grow. Crack will start grow. Crack will start grow. So the case 1, case 2, case 3. Load is same, material is same, geometry is same, all are same, 3 specimens. But the crack length is here, okay, L, okay, here L plus del, here L plus 2 del. Only the length is more. If that is the case, once you study, okay, the increment, the crack increment for these 3 cases, it looks like this. The crack will grow. The crack will grow. the crack will grow, but you can see here, okay, here what happened, delta P1, P2, P3. Yeah, here what they did, crack length is same for all the three specimens. I'm sorry, the crack length is same. Load, 3 loads increased, okay, 3 types of loads. Crack length same only, because you can see here A only, but here it is, okay, P, here P1, P2, P3. So P1 is greater than P2, okay, P2 is greater than P3. So what will happen when you apply P1, okay, with less N, because number of cycles less to crack quick. When P3 is the lowest one, okay, same material, same crack length, same thickness, same geometry, everything same, but it took little bit more cycles to crack to grow. Crack to grow. I hope you got the point. 3 specimen for time being, it has been considered in this graph. So what will happen? Your load is more, P is more. It will take less N to start the crack to grow. Why? Because intensity is more. The P is less. It will take little bit more time than P1. After some time, it will start grow to crack. So this is the phenomena. It has been studied. So this kind of test people used to carry out. Same material, same the same material, same crack length, everything same. Okay, so this kind of study will help them. They can make, okay, a data called dA by dN, log scale, with respect to log K. So this this is the slope, dA by dN, dA by dN. Okay, change of crack with respect to side K. So this is very important graph basically. This is very important. So this is something like a constant called C, a linear constant called C. So these kind of things in future, this data will be useful in the crack study analysis. Crack study analysis. Here, if you see schematic representation of the fatigue life showing the relative proportion of life for crack initiation and propagation. This is, okay, SN curve. What is this? This is SN curve. I told you, no, other day, SN curve. This is log scale. This is life, fatigue life. Fatigue life. So, if I have 2 specimens, same specimen. One is more crack length, one is less crack length. Okay. So, the the less crack length is the green color line, because, okay, in every you can study with the different types of load. Okay, initially you have more load, okay, then you will have failure here. At the same load here, failure is here, because less time it will happen. Here it is more time. Then same one more set of specimen. Okay, less load than that. Then it will fail here, that will fail here. Then one more specimen you take. Okay, again reduce the load. It will fall here. One more specimen. One more specimen. Okay. Then again a specimen you take, you apply smallest load. In either case, there won't be any failure. Now you plot the graph. So what is this difference shows? This difference shows, okay, same material, same geometry, same load, but you need this many cycles required, okay, for this particular load to produce this much crack length. This is the time. What the time? Very important graph this is. First of all, you have to understand how they have created this graph. I told you how they created this particular graph. The next item, what we can infer from the graph. You can see here, crack propagation period. Indirectly we have calculated. This is crack initiation period. Especially this is something like, you know, a crack. Now what is it? There are two cracks. One is this length, this is another length. So this is L, this is L plus del. So L and L plus del. So if I operate this particular stress, it will take, okay, this many time to reach del. So I have a material. I can allow the crack supposed to go from this much length. So how many cycles I can run that particular machine? How many cycles I can run my particular aeroplane? One can easily estimate by studying this kind of graph. Understood?
Yes, sir.
Understood, Paul?
Yes, sir.
Yes, sir.
Okay, these are all very, very practical point of view I'm talking. Okay, so if you have a doubt, please ask me. This is the life estimation. Okay, life estimation.
Sir, in the previous log versus log graph, sir, that
It is only data acquisition. This data will be useful in future.
yes, sir. This del K is intensity, sorry, stress intensity factor, sir.
This is a del K. Yes, this is stress intensity factor.
Okay, sir.
K, yes, you are correct. Stress intensity factor. This it will be useful when you are doing your analysis with respect to fatigue analysis. There, this data is important. One of the parameter. Like when you analyze, you are feeding young smallest, no? In any of your analysis, you are feeding young smallest. Poisson's ratio. Am I correct?
Yes, sir.
Likewise, fracture analysis, the parameter C and delta K and all important. How
Okay,
they
sir.
have generated? This is the way.
Okay, sir.
This is called one another important thing, residual strength diagram. Residual strength diagram. You can see here. Okay, this is crack size. Crack size. Crack means what? I have a crack inside a material. This is the A. I have crack inside the material. Okay, A plus delta. Likewise, crack size A. Or sometimes, they will say this is A. So in this, sometimes they will say 2A. Okay, sometimes the same length people will say 2A or A. So A means half crack length. 2A means full crack length. Whenever, suppose in most of the analysis, we will demonstrate with this kind of crack study. So this is A. Basically, this is what half crack basically. Or one half only we have set. So what the full crack 2A. Okay, so these are all the preliminary before we are entering to this discussion. This residual strength diagram, very important diagram. This crack, this is design strength. Suppose I have a component. I am applying a load. The component is pure component, assuming that there is no crack. Assuming that there is no crack. So I have its strength. That is the ultimate strength, isn't it now? If I apply a P, okay, the maximum I can apply. That is the ultimate strength. That is what? If the component is without any crack or flaw, then I will get its ultimate strength. So that point is here. Because no crack. Now, okay, I have a crack. I have a crack. Now I am applying a particular crack length. Then I am applying sinusoidal load. It will fail one point in time. Then I will get its strength. Definitely that strength, it may not be like this. It cannot be like this. It may somewhere here. One crack length. Then another specimen, same specimen only, little bit bigger crack length. It will fail at an ultimate load. Definitely it will be less than that previous two things. Why this case is my A is more. Then another specimen I will take. Same specimen, still more I will do. It will fall here. Next specimen, it will fall here. So that I can have the graph. So same specimen, same load, but the 10 specimen with a different crack length. A plus delta, A plus 2 delta, A plus 3 delta, A plus 4 delta. So every occasion, if I take the ultimate strength when the material is failing, definitely it will come like this. So I'm mapping with respect to that crack length and failure. So the graph is like this. So I have got the residual strength diagram. Residual means what? When the crack is there, how much strength compared to my original. So what is the use of this particular thing for me? Same material, everything same. The crack length each case is more, different or more. No crack, less crack, more. So that kind of study gives me this kind of plot. From here, what I can infer? Very important question this is. Using this residual strength, I only created the diagram for that particular material which I'm using. What is the use of my diagram? The diagram, what is the use means, it gives here. That means my component, I'm operating one particular P or one particular sigma. This is what my operating stress. In that particular operating stress, how much the crack size I can allow. That means this is my operational stress. So initially, okay, I have one crack length. Okay, that particular crack length will grow. If that growth is equal to AP, I have to stop. Or I have to replace that particular component. Okay. So this is my operational load, and this is my, the permissible crack length. Why? In this particular operation load, I will get this particular up to this is what you call that the permissible crack length. How I can get this permissible crack length? Because I am getting the actual crack length, AC, critical crack length. So some factor, because I cannot, because this is failure, isn't it? For this particular stress, this is failure. I cannot, basically this should not, this is basically AC, but what I want, AP, operational crack length. So I know my specimen, I know my stress. If I apply this particular stress, this is the ultimate crack length which will fail. So how much crack I can allow means I have to find that particular crack length divided by some factor of safety. Definitely this will be, AP will be less than AC. That is my limiting length. So any crack length initially it is there, if it is coming up to AP, okay, then because it's a sigma max, because that's my operational, but initially my crack length is less, but it is growing. When it is coming to AP, then I will stop that particular machine or I will replace that particular component. You got my point?
Yes, sir.
Very important. Okay, this will confuse you, but still these are all the fracture study people used to do in the fracture in the field, real-time field.
Sir.
Hmm.
Sir, then the meaning is that if you are having a structure which has a very small crack, sir, and if for that also the service load will be sigma max only, sir.
Sigma max. Because of sigma max, the crack is growing.
Okay, sir.
How much length I can allow?
That is AP, sir.
So that means how many days it took.
Okay, sir. Okay, sir.
Because here I always monitor the crack length.
Yes, sir.
Or with that growth, I can estimate the number of cycles n. I can do some other thing. From this to that, I can find n.
Yes, sir.
These are all the intricacies of the testing and the inference of the things.
Okay, sir.
Okay, so with that, can we stop today?
Yes, sir.
Okay, sir.
Okay, I'll take the attendance, please. Okay, all the best. Bye.
Thank you,
Thank you.
sir.
Bye.
Thank you, sir.